Today, we're going to be talking about linear models. Okay, we're going to be talking about linear models. Now, we've already talked about linear functions a little bit when we talked about gradient and slope, writing equations, like at the very beginning of the year. So it's almost like, coming back to the beginning, coming full circle to finish out this semester. Okay, but the last lesson that's going to be covered on your midterm is going to be linear models, and this is where you guys are going to basically apply your different properties of linear functions to applications, to real-world applications. All right. So before we actually get to the examples, because as you can see when you open up your foldable, that is pretty much all examples, not that many notes. Because, like I said, we've already gone over, linear functions already. Like, what's the equation of a line?
Y equals mx.
Are you sure it's y equals mx plus b?
It's like 2
C,
1.
it's c, because c stands for the constant, aka the what? The y-intercept. The y-intercept. And the m is the what?
Slope.
Is it the what? It's the gradient. Yes, it is the gradient. Okay, and so a lot of these application problems that you're going to be looking at, they're going to be in the form of y equals mx plus c, where m is your gradient. Remember, that's the change in your y's over the change in your x's. Mx plus c, c being your y-intercept or your starting point. Okay, so don't forget that. Now we're actually going to apply it. So, two variables are linearly related if the graph connecting them is a straight line. Okay, that's what makes something a linear function. So here's an example. It says the graph shows the cost $C of buying X bottles of juice. Before we start looking at the questions, let's take a look here. Okay, being able to interpret the graph to make sure that we could potentially answer these questions is always good. As we can see here, when there are 0 bottles of juice, it costs $0 to make 0 bottles of juice. That makes sense, right?
Yeah.
Okay? But if we look forward, this point basically represents what?
1 bottle of juice. Like 1 bottle of
Yeah.
$2.
One bottle costs about $2.50. Costs $2.50. This point up here costs $5, and so on and so forth. Okay? So we basically have 1, 2.5. Sorry. Actually, we have 0, 0. 1, 2.5, 2, 5, 3, what? 3 bottles cost how much?
$7.50.
$7.50, and then 4 bottles cost
$10.
$10. Okay? As you can see, the x's are increasing by what?
2.5.
The x's.
Oh.
1. Your y's are increasing consistently by 2.5, so this is a linear model. And it's asking you for part A to actually find the model that connects C and X together. C is which part of y equals mx plus b? Like this C, I'm sorry. Like the $C. It represents not your y-intercept, not your gradient. If I look at y equals mx plus b, mx plus c, and in this case, we don't have x and y, we have x and c. C would be what, and I'm talking about c as in cost, would be what part of this formula? It would be your y, okay? So it's be y equals mx plus lowercase c. M would be what?
X, like the bottom.
No, not the bottles. Remember, M represents your what? It represents your gradient. How your y's change in respect to your x's. And I asked you before I went to this question, I said, how are my x's changing? You guys said by what? 1. And I said, how are your y's changing? Every time, right? Consistently. So if gradient is the change of your y's divided by the change in your x's,
So then the M would be 2.5.
your n would be 2.5. It technically would be 2.5 over 1, but 2.5 over 1 is just 2.5. So your gradient talks about how it's changing over time or over the number of bottles of juice that you make, or that you buy is how much you pay. What does C represent? The lowercase c, which is what? 0. So I'll technically I'll put plus 0, but you don't need to. So then this would be your model for the cost of buying X bottles of juice. Is this model exact or is it an approximate? It is exact. This one is exact, and you know it's exact for what reason? What about the graph?
It's always stay constant, as in like every ball is 2.5 or 250. No.
250 more, right?
Yeah.
Yes, it is exact. Think about approximate. When you hear the word approximate, what do you think of? Almost. About, close to, an estimate. This particular line, though, goes through every single point, right?
Mm-hmm.
So when you have 1 bottle, 2 bottles, 3 bottles, 4 bottles, so on and so forth, that line, that equation is actually producing the corresponding y value that goes along with it. So it's exact for that reason. I could write that out, but I just said it. Question?
So what would it look like if it was approximate?
You're going to see. That's coming up. Yes. So to explain your answer in your words. In your words.
Could you say it's approximate because of the 0.5? Like because we don't know that it's exactly 0.5.
True. But I am telling you it's 0.5.
Okay.
But I see what you're getting at because like we don't know exactly if it does fall halfway, but it does fall halfway. And more so it's just because of the fact that that particular equation does go through every single point. That's why it's exact, not approximate.
Could we put like approximate because it's not including tax or something like that?
No. Don't include that. It's kind of like when we look at years, we only do 365. We don't look at leap years. Ready?
Yeah.
Today we're talking about linear models. You guys are going to learn how to apply linear function properties to applications. You guys have done this before when we were going over gradients and equations of lines. Now we're just applying it to the real world, okay? So, what is the equation of a line?
Y equals ms plus
C. Very good. Where the m represents the what?
Gradient.
Awesome. And C represents the
Y-intercept.
the y-intercept. Very good. And so basically all the application problems that we're going to look at for linear models is going to be in this form, where you have y, your dependent variable, x, your independent variable, with the respective gradient, how quickly a line is either increasing or decreasing, plus C, your y-intercept, your constant, basically your starting point. Remember, gradient is the change of your y's over the change in your x's, or basically rise over run. Okay? It's going to be very helpful when we're looking at these different types of examples that deal with linear models. So, two variables are linear related if the graph connecting them is a straight line, like this example here. The graph shows the cost, C dollars, of buying X bottles of juice. Now, before you start looking at the questions, look at the graph. As you can see, your x-axis represents your number of bottles, and your y-axis represents the cost of each bottle purchased. So right here, cost represents the y in your equation, and bottles still represent your x. Now, 1 bottle of juice costs how much? $2.50. 0 bottles of juice. Let me start with 0. 0 bottles of juice costs how much?
$0.
Which makes sense, okay? If I go in the store and I don't buy any juice, I don't spend any money. But 2 bottles of juice, 3 bottles,
$7.50.
and 4 bottles.
$10.
Now, as you look at this, as you look at each one of these points, your y's are increasing by how much? 2.5. Your x's are increasing by what? 1. And when it comes down to writing the model connecting C and X together, the change of your Y's over the change in your X's represents your gradient. So that 2.5 over 1 is going to represent your M. C is going to represent what in your equation?
dy intercept.
No.
No.
Capital
Cost.
C.
Oh, why?
Your Y, your dependent variable. And what is my Y-intercept?
0.
0. Okay? So actually, let me write it out a little bit better. So in that way you can see. Normally we have Y equals mx plus C. However, in this case, Y is our cost. X is our number of bottles. Our gradient is 2.5. And yes, our constant is 0. So I really don't have to put anything for that. Now for B, it's asking you, is the model exact or approximate? Now in this particular case, even though, yes, we are making the assumption that that point is halfway, right here at 2.5, and of course halfway at 7.5, this is still an exact model, okay? This is still an exact model because every point on the line is increasing, because the line is going up, the cost is going up, is increasing in a consistent manner, okay? So because your graph is increasing at a consistent manner, that model is an exact model. I don't have to write that, it's just said, so you can write that down. Now, because it's exact and we know it's going to continue to increase in that same fashion, we can use the model to predict or use the model to find the exact cost of 12 bottles of juice. So to find that, what are we going to do?
Plug in 12
We're going to plug in 12 for X into our model. So what's 12 times 2.5? $30. $30. Make sure you don't forget your units. And so yes, we can use the model because this model is an exact model for this linear situation. Question? Now let's look at this. This is what happens when a model is not exact. As you can see, the points and the line that go through them, the line doesn't actually go exactly through the points. It's like the points are close to that line. As punishment for misbehaving, Jack is picking up litter at lunchtime. This table shows how many pieces of litter he's picked up after T minutes, and the graph alongside shows these data points as well as the linear model n equals ht plus 0.2. When you look at this graph, this one clearly is not exact. It's an approximate model. And look at your table. Look at your table of values. To go from 8 to 18, how much did you increase?
10.
10. To go from 18 to 23,
5.
5. To go from 23 to 30,
7.
to go from 30 to 42,
12.
12. This right here, that's not consistent. If anything, you can almost even look at it like an arithmetic sequence, okay? If it was linear, like arithmetic sequences are, it would increase at consistent increments, which this one doesn't. So, again, that's the explanation of your answer. You can write it out yourself. Now, it says to use the model to predict how many pieces of litter Jack will pick up in 20 minutes. I'm going to plug 20 into what?
X.
Which variable?
T.
You're going to plug in for T because 20 represents your time. So N equals 8 times 20 plus 0.2. And how many pieces of trash is that?
160.2.
Now discuss the accuracy of your prediction. Now because this is an approximate, anything after 5 minutes is called an extraploitation. Any time after 5 minutes is an extraploitation. Extraploitation. That basically means that we don't know what's going to happen after 5 minutes. This was an approximate model. So for all we know, what could happen?
You can stop picking up.
You could run out of trash to pick up. So that means that it actually could be very constant after a certain amount of time. He may only pick up one piece of trash after a certain point in time. Okay? So because of that, the IB likes to trip you up with these types of problems. So when it is an approximation model or an approximate model, and it asks you for anything that's outside of the given time period that the equation was based off of, you cannot actually find the answer. Even though, yes, we could plug 20 into the equation and actually get a value, we do not know if he is indeed going to still have 160 pieces of trash that he's picked up after 20 minutes. Does that make sense?
Mm-hmm.
Somewhat? Yeah? Okay. Is there anything else I want to say about this? So, let's take a look. The cost of printing invitations depends on the number of invitations printed as shown in the piecewise linear model. Now, this one is different from the other two, okay? Because, as you can see, from A to B, it's one line, but then from B to C, it's a completely different line with a completely different gradient. Yes?
Yes.
Yes. So, because of that, I am asking you, part A, to find the gradient of AB and the gradient of BC. So, what's the gradient of AB? 1? Gradient is 1.
Yeah.
What's the gradient of BC? 3 over 5? 3 over 5. Okay. So interpret your results. Interpret basically means in context. I feel like this is, deja vu. I feel like I said this before. In context of the problem, when you have a gradient of 1, what does that mean?
One invitation costs $10.
So,
Accurate?
you're on the right track. It needs to be in context of the problem. So when she said, she said one invitation costs $10, you are on the right track, but not quite. This point right here doesn't correspond to one invitation. It corresponds to
20.
20.
And the y is 10.
and then the y is 10. So actually for every, so if that's the case, the gradient shown up is not 1.
It's 20. It's 10 over 20, so it would be like 1/2.
Not 1/2.
Or 10 over.
Ooh, Lord have mercy. A is located where? 0, 0, right?
Yeah.
Where's B located?
10, 20.
100.
100 and then 50, okay? So how do you find the gradient?
Y2 minus y1 over x2 minus x1.
So, Christian, sorry, you were right. It should actually be what? 1/2. Okay, so now that we have the correct gradient in context of the problem,
For A2 I got.
wait, no, we're still on A1.
Okay.
We got to interpret the results for A1. So, for every 20 invitations, it costs, is it 10? Yeah, it's $10. $10. Up until when?
100.
Until 100 invitations. Because what happens after 100 invitations? The gradient changes. Now the gradient is 3/5. So what does that mean? The price does decrease. So now it's
Every 200 is $80. I think it's 3 I do too. Yeah.
That's what I
so
got.
this was wrong too?
Yeah.
Cool. All right. Okay. So let's fix this. Let's fix this one too. C is located at 280.
Yes.
Okay. So now we're doing BC. That's 80 minus 50 over 200 minus 100. Yes?
Yes.
You sure?
Yes.
Yes.
Yeah.
It was 80 minus 50.
30. Take off the 0.
So this is 3 over 10. So now this is saying for every, how many invitations? For every 10 invitations, how much does it cost now? Not $30, $3. Until when? 200. Because after that, we don't know what's happening. We know it's still continuing to go up. We don't know if it continues at 3/10 or if it continues at something completely different. Okay? So, careful on finding your slope because your interpretation is going to be based off of that. And that usually makes sense. A lot of these companies, they'll give you a flat rate for a certain amount and then they'll start to charge less the more you get. Okay? Now we need to find the cost of printing 60 invitations. Okay? Find the cost of printing 60 invitations. Since we don't have a model here to plug 60 into, we use the graph. 60 invitations. That hits your graph at this particular point. How much am I paying? $30. And that's using the graph to interpret, using it for interpretations. What about how many invitations can be printed for $74? About 180? I think that's a good guess. In these particular cases, they'll give you a range that you'll be able to fall in between. So 74 is right above 70, a little less than halfway. And that would be 180 invitations. Very good. Questions with the piecewise? Find my slope accurately. Okay? Find my slope, my gradient accurately. Students. Here we go. The table shows the income tax rates in the UK in 2018. This time we're actually going to draw the graph of tax paid against income, and we're going to find the amount of tax paid by a person who earns £50,000 per year. Okay? So we have this data here that represents taxable income per year and the taxes paid. So when we create our graph, we need to figure out what is our independent variable. What's going to go on our horizontal axis?
Income per year.
It's going to be that taxable income per year. Remember, your x-axis is your independent variable, the thing that will always happen no matter what. Your income is going to be taxed. That's going to happen regardless, okay? But your taxes paid is based off of how much you make. Hence why that is your dependent variable. Whenever you have to create or draw a graph yourself, you always want to make sure that you label your axes if they have if they actually have like titles like they do in this case. And then of course you want to make sure you do a scale. Sometimes they'll give you the scale. They'll tell you how much they want it by, but if you ever have to do it yourself, you want to make sure your scale is consistent. Okay? So let's look at our x-axis. We have up to 11,850. We have between that and 46,350, so on and so forth. Okay? So clearly we're going to start at 0. We're going to go all the way up to 150,000. What do you think is a good scale for the bottom?
No.
And I'm going to pause this because we're going to throw out some ideas.
Are we supposed to divide up the taxable income more than 4 sections?
So one thing that you hopefully you notice between each of these sections is that they're not the same size. So because they're not the same size, we can't like say that, okay, well, we're going to equally say that 5 lines is going to be, 11,850. And then 5 lines is going to be everything in between because they're not the same size. If they were divided up evenly, then we could do that. But because of this, we're not going to be able to do it based off of these particular values. But what we can do is we can take the full spread and divide that equally. Okay? So 150,000. How many lines do we have on our x-axis that's given to us?
20.
We have 20. So
7,500 for each.
that's the even?
Yeah.
Okay. Is that good, you think?
Yeah.
You want to do every 5 lines? What? You said divide by 5 or divide by 4?
Well, each line would be 7,500 to get to 150,000.
Okay.
So you can do like every 5.
Okay. Let's see. Every 5. So what's
I have 19 lines, not 20.
Yeah, 19.
from where this axis is?
If you look
Okay.
from the y-axis over.
So that's 19. Okay. Well, we'll still run it that way. We'll still run it that way. No, let's not run it that way. Move your y-axis. Move your y-axis over on your graph.
Why 19 makes it so
Oh, okay.
This is why a lot of times I don't give y'all graphs mostly.
I'm just gonna add another.
There you go. So we're gonna use this, and we're not gonna use the other one.
We bootleg in like.
There you go. Okay. So now we do it this way. Now we're good. So every 5 lines, because mine is really small. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay.
Every 5 would be 37,500.
So then what's my next one?
Um, 75000. 11250. And 150.
All right. So we know that for the first little bit, you don't pay any taxes. So if you make less than 11,850 pounds, you don't pay any taxes. But then in between that and 46,350, you pay 20 cents for each dollar. So I have a question. If I am paying 20 cents, or not dollar, if I'm paying 20 cents for every pound up until $46,350, then how much in taxes does somebody who makes $46,350 is going to pay?
Can you repeat that?
Yes. If I have to pay 20 cents for each pound in this particular range, then if I make 46,350 pounds and I'm paying 20 cents per every pound, how much am I paying in taxes? 6,900. So if I'm at the high end of this, basically this tax bracket, that's how much I'm paying in taxes.
How'd you get that? Like, what math?
How'd you get that? Whoever found it?
You subtract the minimum amount. So you would take 400 or 46350, and you would subtract 11,850, and that's the amount that's above 11,850. So you would multiply that by 0.2.
I just multiplied 46350 times 0.2.
And did you get that?
No, I got 9270.
But it is that amount though, that distance. So however much is in there, that's how much. This is for each one above it. So you are going to need to subtract and then multiply. So because our y-axis is representing the taxes paid, we have to figure out exactly how much is paid. Okay? So it's 20 cents per each pound above that amount. Now for the next range, they're paying that 6,900 plus 40 cents for each pound above. Okay? So following a similar process, let's figure out how much in taxes does somebody who's in this tax bracket pay. So then you have 48,360. And then what about over 150,000 pounds? Let's figure out how much they're going to be charged in taxes. Well, actually, are we going to be able to figure that out? No, because it's saying everything that's greater than that. So they're going to pay 45 cents per each one after that. So now that we have this, and we know that this one is at the very low in the 48,360, we can go ahead and graph this model.
I have a question.
Yeah.
So if someone made $150,000 150,000, would they pay for with the middle bracket? Or just figure it out?
Yes.
Okay.
Is when they make 150,001 pounds. That's when they start going over. That's when they're in the highest one. So when someone makes no money, do they pay any taxes? No. Okay. But and then also if they make 11,850 pounds, how much taxes do they pay?
None.
They still pay none. So 11,850 is bigger than 3,750, but less than. No, it's not. It's less than 37,500, right? It's 2 zeros. So it was 2 zeros. That's what was throwing me off. I was like, oh, okay. So 11,850. Basically, anybody who's within this part pays 0 pounds in taxes. But after that, they're going to pay 20 cents for each pound above. Now, we do know that somebody who makes well, that's actually how much it is. How can I represent the second bracket? From everybody that's from 11,851 to 46,350. How can I represent that? How much in taxes do they pay?
Did you just do like the average?
General increase.
It's generally increasing, not the average. How much is it increasing?
0.2 pounds for every dollar. So
0.2 pounds for every dollar. So that means our line is going to start to go up. And then once it reaches this point, this 46,350 pounds, what is its, how high has it gone? 6,900. So then that's going to be basically our stopping point for that particular piece. Okay? So we need to go ahead and label, I just realized we haven't labeled our y-axis. We need to label our y-axis here. What's a good breakdown for this? We can see our orange is going to represent our y, so we don't need to go up too high. 50,000, okay. So you want to go what? Every 4 lines, 10,000? So, 1, 2, 3, 4.
Would this be like a short response question?
Okay, well, to be honest, it really could depend. Because if they give you the scale, then it could be a short response question. But we had to create ourselves. So now I need to apply 6,900, which is a little less than 10,000. And then I have my next piece. How do I represent that third segment? This is the largest one. At my highest point of 150,000, 48,360. That's why I had you find those numbers, because those were basically our y coordinates for each one of these x's. So 48. And what happens after that? It doesn't stop.
Everything over that you have to pay.
So you narrow
because it's still increasing, but it's not increasing like how it is for that one because it's 40 cents per each. It is 45 cents. So this right here is our piecewise linear model to represent the taxes paid by someone who in the UK in 2018. So the main thing in this when it came to the graph was that our Y's were our taxes paid. We had to figure out what that was before we could actually have graphed it. Okay? And that's what we did, which is in the orange, which I had you do when you multiply by 0.2, multiply by 0.4, so on and so forth. Okay? Now we're asked to find the amount of tax paid by a person who earns $50,000 per year. Now because you created this graph yourself, you use your graph, because we do not have an equation here, to estimate how much taxes a person paid when they earned 50,000 pounds in a year. So we need to go to 50,000 on our which axis? Our x-axis, and then draw a vertical line to see where it hits our graph, or your graph, the one that you drew on your paper. And then we're going to draw a horizontal line over to see about how much they paid in taxes that particular year. Okay? So find where 50,000 is on your graph, and then where it hits on your y-axis. I'm going to edit my graph a little bit. What did you guys get? About what? About 8,000? Less than 10,000, yes?
Yes.
Okay. Same with mine. Mine was going to probably be a little bit somewhere around 9,000 pounds. Okay? We do know that this falls in the third tax bracket. So we know we're paying 69,000. Or 6,900, sorry, and then 40 cents for each one that's above. So if I'm making 50,000 pounds, how much more is that? 3,000 what?
600.
Teachers and students.
Good morning. Good morning. All right, so let me finish up this problem. So that's how much we are making additional. So then we're going to multiply this. Another way that we could do is multiplying it by 0.4. What is that? 1,000 what? 460. That's additional on top of the 6,900 that we would have to pay. And what do you get? 8,360. So pretty close of a graph if you got something that's literally from your graph that is below 10,000. Okay? And so, here it didn't specify using the graph or using the table, so either one would have been acceptable of an answer. But that's how you would do it for both, using your graph and using your table. Okay? Main takeaways from this lesson with your linear models, okay? If it is exact, it should follow y equals mx plus c, a linear equation, okay, where you have a consistent slope and a y-intercept, okay? You can also have approximate linear models, which are your best models for whatever the situation is, okay? There's also your piecewise linear models, which are comprised of different linear functions made into one, like this one and also the one about the invitations, okay? But no matter what, whether you're given an equation or not given an equation, you can always use your graph to answer, estimate, or predict different values. Questions?